I apologize for so rudely interrupting your lunch, but I'm really grateful you're back, and I'm glad to be back, and I'm glad we have an outstanding lineup of presentations coming at us this afternoon. And for the next hour, our theme will be water in all of its different forms and power and changing of phases and interacting with waves and all that stuff that helps not only make for climate change, but makes for a habitable Earth, right? So we will start with Anito Marcarelli, and his presentation is about these things called atmospheric rivers and the West Antarctic sea ice variations. This is a very interesting and important topic that will, if you think about this, the ways in which complex systems are connected are not always obvious or visible, and I think the impacts of atmospheric rivers are an excellent vehicle through which to see how the impacts of teleconnected things can intersect and lead to really interesting nonlinearities and exacerbate climate change impacts. So Anito is here to talk about these mechanisms. Anito, the floor is yours.
Okay. Hello, everyone. Before I begin, I just wanted to say a big thank you to my advisors, Dr. Arthur Miller, my capstone chair, who really helped me with this project. He was very engaging, very welcoming, very knowledgeable, but most importantly, he really introduced me to a lot of great scientists, such as Dr. Matt Maslow, who's here today. Thank you for coming, Matt. Dr. Christoph Rankel from the University of Bonn, and Dr. Jerry Zhao, who is from CW3E, who both of them join us virtually. And so my talk is about atmospheric rivers and West Antarctic sea ice variations. Okay, let's begin. So what actually is an atmospheric river? Atmospheric rivers, or ARs, are these long, narrow, transient corridors of water vapor transport. They're usually formed in the mid-latitudes, where the intersection of the cold polar air meets the warm tropical air and forms these strong winds. These strong winds can actually sometimes pick up evaporated water vapor from the tropics. They're very, very, very important for our climate system, especially here in the US West Coast, where roughly 30 to 50% of all precipitation events are actually attributed to ARs. And 40% of the Sierra Nevada snowpack is actually also attributed to ARs. And anytime you see any sort of flooding in some of California's river systems, such as the Russian rivers, it's likely due to ARs as well. ARs are expected to increase in frequency, intensity, and duration in a warming climate. So it's very important that we study how these systems work. A very important metric for atmospheric rivers is this thing called the integrated vapor transport. So if we can recall, ARs transport these kind of warm air masses poleward. So it's kind of important and useful to come up with a metric that defines how quickly and in what direction and in what magnitude this water vapor kind of moves around. And that's exactly what IVT is. I won't go into the mathematics of it, but it is essentially a very defining metric for ARs, and the typical threshold that defines an AR with the IVT is about 250 kilogram meters per second. So on this diagram here on the left, I actually have a plot of IVT here. As you can see, here's an AR kind of moving towards the US West Coast, moving forward in time, and you can kind of see its motion. So ARs are very important because they transport sensible and latent heat. So what is sensible heat? Sensible heat is the transfer of heat from a warm surface to a cold surface. In the atmosphere, they're dependent on wind speed and the temperature gradient, so the difference in temperatures. Latent heat is the transfer of heat that occurs during a phase change. So think of your precipitation, think of melting, boiling, condensation, stuff like this. It is very typical to define a radiation flux as downwards being positive. And so what I mean by that is heat being dumped from the atmosphere into the ocean. That's the kind of a downward positive direction. So if we turn over to these maps here, in the first map I have latent heat flux plotted, and as you can see here, there's negative values in the tropics. So that means that there's more heat coming from the ocean into the atmosphere. And so that what kind of implies is that that's actually indicative of evaporation. So that's kind of how we can see kind of physical processes even within heat fluxes. So it's kind of really interesting. If we go over to sensible heat flux and we kind of move over here into our region of the eastern United States, We can again see kind of a negative sensible heat flux, so that would imply that the temperature gradient is stronger at the seas, so the ocean is actually warmer than the atmosphere, and that can be physically interpreted as actually the Gulf Stream, which you can actually see plotted here just by using sensible heat. So it's kind of very cool and interesting, and it's important that we understand directionality moving forward. I think there might be an issue. Oh, there it is. Okay, thanks, Jada. Okay, so in Antarctica, they only occur for about 15% of the time, so they're quite rare. However, they really attribute to a lot of the surface mass balance melting, which Trevor touched on, and which holds about 58 meters of sea level equivalent, which Isha touched on. Not only that, ARs can trigger very, very extreme heat waves, and in some cases, such as the March 2022 AR event, left the East Antarctic Peninsula with temperature anomalies of 30 to 40 degrees over a land region that is roughly equivalent to the Colorado Desert. In the Antarctic, sea ice is a very crucial component to the climate system. It helps regulate gas fluxes, heat fluxes. It's very important for stabilizing the ice shelves, and of course, it's actually also very important in shaping the ecosystem. There has been a significant decline and a constant decline in Arctic sea ice extent, which Trevor touched on earlier on. However, in the Antarctic, we've actually seen kind of opposite trends. We've seen a statistical increase up until about maybe 2015, where we saw this kind of massive, massive decline, and now it's starting to pick back up again. So it's kind of very interesting, and I think what this kind of really highlights is that we don't really understand how Antarctic sea ice actually works, and that more research needs to be kind of done, which kind of led me to kind of look at Antarctic sea ice, primarily in the Antarctic Peninsula, as Trevor touched on also. The Antarctic Peninsula has warmed by 3 degrees since the 1950s. So what I have plotted here is a map of West Antarctica with its surface temperature anomalies. So this is the April 2025 relative to a climatological average. So red means warming. As you can see here, there's a lot of heating going on in the Antarctic Peninsula. And in fact, it's lost about 28,000 kilometers squared of ice shelves also since the 1950s. So we've seen like huge decline in ice shelves in this kind of region here. Interestingly enough, the Amundsen and the Bellinghausen seas, which are here, feedback loops here can actually also interact with the ice shelf, kind of causing further melting. And again, the Amundsen and the Bellinghausen seas are also where sea ice is produced, kind of further kind of asking these kind of questions. And again, ARs then in the Antarctic Peninsula, what actually occurs here? Well, ARs cause about 40 to 80% of the recorded melt days in the Antarctic Peninsula. The way this kind of warms is usually done by something called foam warming, which is the movement of this vapor. It's coming in, all of a sudden it's hitting the Antarctic topography, so the mountains, it's forced upwards. And as the water parcels are forced upwards, it has to precipitate. And in precipitation, there's a phase change, which we just spoke about earlier, leading to latent heat release. Again, these parcels then begin to kind of drop down very fast on the leeward side, and as they drop, they heat dramatically, and this is the effect of foam warming. On average, the temperature of the leeward side of the mountain is about 3 degrees warmer than the windward side of the mountain. Furthermore, there's also kind of other feedback loops with this kind of foam warming attributing here. For example, when melting occurs, water can actually seep into crevices and form these things called melt ponds. And melt ponds lower the albedo of the Antarctic, which again would then heat the whole system, heat the system more because there's less reflection going on. There's also cloud formation here, which affects how much long-wave radiation can actually escape. So trapping more long-wave radiation, again, leading to more heating. And of course, ice shelf activity collapse has also been linked to ARs, kind of to these processes that we just kind of spoke about. So with this, I kind of wanted to ask the research question of how do these atmospheric rivers affect the local sea ice in the West Antarctic Peninsula? On the left here, I have the region of interest plotted here, overlaid with the 2-meter temperature anomalies, just to kind of give you an idea of what we're doing. So what did we actually do? We decided to look at the months of January and June between 2017 and 2024. I want to just note here that January is local summer and June is local winter. So we decided to look at these months and these years. We used ERA 5 data set, which is a reanalysis product. Reanalysis is just a fancy word for models that predict long-term time series of variables given a small set of observational data. We then decided to look at the top 5% latent heat flux and the top 5% sensible heat flux events. Again, downwards is positive, I just want to remind you. And then we split the events into ARs and non-AR events. And the way we did this was using the target version 4 algorithm that was developed by Bing Guan and Dwayne Walliser, and partially also here at Scripps. And it defines an AR based on its IVT magnitude, which we just spoke about earlier, its geometry, as well as its lifetime. However, in the interest of time, I'm just going to speak about June and the latent heat flux results. However, the rest is all in the report. Okay, just to kind of have a brief overview of what we're seeing here. Here overlaid is the sea ice concentration in the color map. Sea ice concentration is basically just defined by what fraction of the grid is covered by sea ice. So we can see here, there's a lot of sea ice here in the Weddell Sea, and then it slowly kind of starts to kind of fizzle out, and then it kind of hits the open water. And the same kind of thing we see in the Amundsen and the Bellinghausen seas. I want to now draw your attention to the vector maps. Here, the vector maps are showing wind and wind speeds and wind direction, and these are actually been nicknamed the Furious 50s, which are these kind of strong westerly winds that we see throughout, and these actually kind of cause a lot of the ice formation in South Antarctica, which has already been touched on in other talks. You might be asking yourself, why is there more sea ice in the Weddell side as opposed to the Amundsen side? This is because the Weddell Sea is trapped by the peninsula, and so it's kind of more exposed to the cold Antarctic air. So this cold, dry air is kind of coming in, and it's kind of hitting all this thing here, and we can see it here. We can see the air kind of moving from the south towards the north, and this is like perfect breeding grounds for sea ice formation. Okay, so what's the first thing we actually decided to do? The first thing we did was we looked at the 2017 to 2024 June AR events only, with no constraints. So we wanted to see the fraction of time that a grid point was under AR conditions given the target algorithm data set. And what we see is that we see about a 26 to 28% fraction of time activity here in the Drake passage, and then it kind of slowly begins to decline into like your 10, 14, 16%, which also is congruent with the literature. On the right, I have plotted a contour map, just to kind of give because we will be using this later on, so I kind of want to just talk about this for a minute. So here, for example, we see an interface between 26 and 28%, and on the contour map, that's kind of plotted like this. If we use another example here, we have 16 going to 19, and then when we plot it on the contour map, we also see 19. So that's kind of how this contour map works. Okay, so now we want to look at the LHF, or the latent heat flux events. And what we decided to do was we decided to plot the fraction of time the latent heat flux events were under AR conditions. So as you can see, it's like drastically different. So again, here's the contour from the previous slide, and you can see it's like anomalously high, even relative to the normal AR count. And this kind of is implying that there's a high AR occurrence when examining the top LHF events, which is quite interesting. So then we decided to look at the sea ice and surface wind speed anomalies. So over here, I have them plotted with their AR components and their non-AR components. I want to just very briefly draw your attention to the color map here. What's this actually showing? Well, red is indicating that there's a higher sea ice concentration, and blue indicates that there's a lower sea ice concentration. But lower, what does higher and lower mean? Relative to what? Well, it's actually relative, again, to the climatological average here. So it's very interesting, like how we can see all these kind of splits here, and I'll speak about them briefly. Starting with the winds, we see strong winds here in both cases, which is very interesting in the non-AR cases as to why they're very like poleward, whereas in the AR it's expected to see poleward wind speeds. However, if we can recall, LHF and latent heat flux events are dependent on wind speed and humidity. So having high wind speeds is obvious if you want to have high latent heat flux events. Moving forward to the sea ice concentration again, we find that there is a lot of melting here and a lot of loss in this blue region here. However, there's no buildup of ice here. It kind of just disappears. So that's kind of indicating that maybe the sea ice is melting here in the AR cases. However, in the AR cases, we see melting in the same kind of regions. However, we see an anomalously low sea ice concentration in these regions, but we see an anomalous buildup here of sea ice. So this kind of suggests that maybe there's some sort of pushing event, so the dynamical component or the winds push the ice more as opposed to the AR events. And yeah, so there's more melting in the AR events and there's more pushing in the non-AR events. However, we do want to highlight that there's some things that we're still working on, such as interannual variability. So the southern annular mode is one of the biggest variability things here, and that is the upward and downward movement of those westerly winds that we saw earlier on. We kind of only looked at a really small time period. This was kind of done kind of in the name of computational time, to not be too computationally intensive. We also are yet to look at wave dynamics and how they're coupled with ice motion, which would probably kind of give us a better idea of how this kind of pushing or the advection would kind of occur. So what did we actually end up finding? What's our conclusions? Well, in both January and June, however, I've only showed June, we see a decline in sea ice concentration in the AR cases. Our results show that in the AR cases, we see much more melting of the sea ice. In the non-AR cases, instead, we see much more pushing than melting in the sea ice. And this is kind of suggesting that maybe the thermodynamical component of ARs might actually be the bigger player here as opposed to the dynamical component. And this is something that is kind of going against the literature, and so we're kind of working on interpreting these results. Here are my references. I'm just going to leave you with the conclusion. Before I conclude, I just want to say thank you very much, Corey. Thank you, Jada. Thank you, Mark. Thank you, everyone, for being here. Thank you to my cohort, and thank you to my family and friends for coming. So I appreciate that a lot. And with that, I'll take questions. Thank you. No questions. Cassie.
Hey, thank you. Fantastic presentation. Quick question about ARs
Yes.
in the Antarctic. What type of precipitation is falling, and do you see changes between June and January predominantly, and how that could affect the melting or non?
Precipitation we have modeled here. I think I had them in the supplementary slides. Yeah, so here is January, and here is, maybe I don't have June actually plotted. But yeah, I think we did see a tiny bit of change, but not that much. And especially even in snowfall and rainfall, we didn't really see much of a change, but that's also the ERA 5 data set is not the best maybe for precipitation data. So yeah, we haven't looked at MERA 2 yet, but that's kind of where we're going to go next.
All right, thank you.
No worries. Yeah.
I was just going to ask about the frequency of atmospheric river occurrences over time, like if you've seen an increase in just how often it's occurred, and perhaps just like maybe an example of how we can see that impacting us here, maybe with like the extreme rainfall I think we had, what was that, last year or the year before? Mm-hmm. And how is that related, just how it relates to San Diego.
Yeah, it's kind of interesting because in a warming climate, we're going to have more vapor. So kind of one of the big questions is, how do we define the IVT metric? So it's kind of difficult to actually properly quantify. And a lot of work is being done, especially here at CW3, in trying to predict future frequencies. But I think the 2023 event is what you're current. That was kind of a family of ARs, kind of one after the other. That's what caused that precipitation. But yeah, it's definitely going to like increase. But yeah, there's still work being done on that. Okay, thank you.